Okie doke. Things are rolling. That's good. Okie doke. So let's get started then. We kind of last time we talked about light. We talked about how atoms can absorb light and emit light of certain wavelengths, and that different atoms from different elements have different wavelengths that they're able to absorb because their energy levels will allow for it. That being said, that kind of is going to be put aside right now, and we're going to be talking about specifically just electrons today. And so we're going to be taking that kind of idea of kind of the old model to the new and exciting stuff, where we have various different shapes of orbits instead of just that plain circular one. We're going to see we're just going to make fun little flower shapes. So we're going to kind of progress our knowledge from what's called the Bohr model, where we had the nucleus in the middle and we have these rings around where electrons are zipping about and doing things. Honestly, the Bohr model is not bad. It does a pretty good job of explaining things, and so it's a good kind of educational tool, but we have better ones now that we call the quantum mechanical model. Which is going to be our kind of that'll be our most up-to-date understanding of how electrons work. So remember, we're doing this because electrons are going to be pretty much doing all of the chemistry that we see, so it's very important that we kind of understand electron behavior. And so we're going to kind of right now look at electron homes, as it were. So we really actually didn't even talk about much about this stuff until organic chemistry, so it's still good to know, though. All right, so we're going to see that electrons will always kind of behave the same way. So electrons always want the lowest possible energy. As does everything in chemistry. Low energy is an ideal situation. So, good morning, Ed. We're going to see that there's kind of two things that we can look at for having electrons have low energy. One of them is having them close to the nucleus. So the closer they are to the nucleus, they're going to have lower energy. And that kind of makes sense, right? We know the electrons are negative, nucleus will be positively charged. So if the electrons are close to the nucleus, this is chapter 4. That's going to kind of make them happy. All right, and so the other one is going to be kind of the same idea. From other electrons. We want them to be kind of far away from other electrons. And so we're going to see that some of these different kind of houses that we have for electrons are bigger than others. And we're going to see that kind of our magic number is going to be 2. Like each of our kind of like little houses for electrons can hold 2 electrons. After that, it's just too much energy. They just can't do it anymore. They're too close to each other. And that's not ideal. So with these two things in mind, I kind of like to talk about this in terms of like something back in the old day called a concert. Of course we don't have these anymore, but concerts were these things where people would perform music and the audience would, enjoy it. So pre-COVID, right? All right, and so, your concert venue is kind of, if you're to go buy tickets to your concert, you have an option of where to sit, right? And so if you have unlimited money, you'd probably want to sit right up close. And so we're gonna see that this is gonna be the the best seats in the house. Would be up close and personal with the artist. We're going to see that this corresponds to basically the nucleus. And this is going to be the closest electron orbital. Will be kind of the best seat. So the closest that you can get. We're going to see that close area is pretty small. But as we move further away from the nucleus, things are going to get bigger. And so we can actually fit quite a few more electrons in these kind of slightly farther away ones. And we're going to see these are going to be good seats. And then, eventually you've got just like the bad seats way out there. So we're going to see that the farther you go from your nucleus, you're going to have kind of the bad situation. So just in terms of energy, you're going to have the highest energy if you're way out there. All right, so we're going to see that these electrons are going to kind of organize themselves so that they'll always have the least amount of energy possible. And so we're going to kind of talk about some of these orbitals now. So orbitals are statistical kind of models of where we have the best chance of finding an electron. And we're going to see that these orbitals, which are just mathematically generated, they kind of come in 4 different flavors, as it were. We're going to have what are called s orbitals. These ones are spherical, hence the S. And so we're going to have other ones that are non-spherical. We're going to have p orbitals, which look like dumbbells. We're going to have d orbitals, most of which look like this. One of them doesn't, but that's okay. And we're going to have the f orbitals, which are much more complicated. We're not really going to touch the f orbitals in this class, pretty much. We might just show you where they are, but that's probably it. And so we're going to see that electrons will kind of zip around in these patterns. And so for an s orbital, it's kind of spherical, boring. What's interesting for a p orbital is we're going to see that an electron, maybe that dot there, is going to be zipping around in this kind of figure 8 pattern. But what's interesting, though, is that electron can go to the other side of the figure 8, but it never passes through the middle, which is bizarre to us, because we might be thinking, well, hold on, if I want to go, across to the other side, I have to go through that middle area. But quite magically, electrons just don't. They can never exist in that middle area. And so quantum mechanics doesn't make sense to us with regular physics. Of course, if I want to go, for example, to my kitchen or something, I can't go through the wall here. But electrons, they could be in my living room and then just pop up in my kitchen without ever going through the wall. And so it's kind of magical that way. We call these, by the way, nodes. These kind of areas where electrons can't go. You can see that in these different kind of shapes, we're going to have a lot more nodes that are happening. So electrons can kind of go between those circled areas, the white areas that are surrounded by black, but they can't pass through the nodes. But it's okay, they don't need to. They can just pop up on the other side. Magic. So, hooray. So, that's kind of just what these things look like in our best approximation. Of course, we can't actually see these, but mathematically, all the experiments that have been done show that these are kind of our most likely kind of shapes of these. Just so you know, we're going to see that kind of each of these orbitals can also come in different kind of like subcategories. We're going to see the S doesn't have any subcategories, but the P's do. Let's see. The p orbitals can be aligned in any of the kind of graph directions. We would call this one pz, px, py, or I guess it's the other way around, but it doesn't really matter. I can choose my directions whichever way I want. Where these would just be kind of aligned with, you've got your z-axis here, your x-axis here, and your y-axis here. They're just kind of aligned on one of those. And so we're going to see that there are, in fact, 3 p orbitals going on at once. One of them each aligned in every direction. And we're going to see for d orbitals there's 5 and f orbitals there are 7. We'll worry about those in a little bit later. You don't need to kind of memorize any of this sort of stuff right now. We're kind of just building on to how we're going to talk about electrons and how they're configured within an atom. Okay, cool. So with those in mind, we're going to see a couple of things here. That if we look at our kind of Bohr model, each of these rings that we talked about, previously, are what are called shells. Those are going to be electron shells. So we're still going to kind of have the same idea where we have these shells that are kind of built out around the nucleus. And so we're going to see that there are going to be 7 shells that we're going to ever kind of deal with in chemistry. So these are all shells. And we're going to see that the closest one to the nucleus, n equals 1, that is the closest shell to the nucleus. That's the lowest energy one. It's also the smallest one because it's the closest. If you think about these like kind of as shells around it, like those Russian dolls that just pop out. They're smaller when inside. The stuff towards the middle is always smaller. So we're going to see that the subshells within the n equals 1 shell will only be an s orbital. And we call that orbital 1s to indicate that it's in the first shell. All right. If we look at the second shell, we're going to have a 2s as well as a p orbital. P subshell, rather. And if we keep going, we're going to just be adding on more and more various subshells until we get to 4. That's going to kind of be the end there. At level 4, we start introducing the F one. And after that, everything else is just the same. We don't go above F. 5D, 5F, 6P, 6D, 6F. Oops. Technically, we don't really ever see these ones at all. Those don't really factor in for us, but that's okay. Those are just even higher energy. They're not normally filled. And so we're going to see that all of this is terribly confusing, right? Don't worry, we'll get through it. All of these would have kind of limits of how many electrons can be stored within them. And we're going to see that any s orbital, subshell rather, can hold 2 electrons. P subshells hold 6 electrons. D hold 10. And F will hold a maximum of 14 electrons. And so we're going to see that, I'm just going to erase this right now. By kind of understanding this, we're going to be able to kind of very definitively talk about what kind of types of electrons are within an atom. Because we're going to see that electrons in an S subshell will kind of react differently than ones in a P, or ones in a D, or ones in F. And so it'll be important for us to kind of identify kind of types of electrons. So, your brains are fried already, I'm sure. Don't worry, this is probably the hardest conceptual topic, but it all boils down to something that's not terribly hard. So we'll get there. Don't worry. So, we're going to see that we can actually use several different kind of tricks to talk about the electrons within an atom. Let's just look at, first off, a couple of easy atoms here. Let's talk about hydrogen and helium. If we look at the periodic table, hydrogen has 1 electron. Helium has 2 electrons. These being low electron atoms make it easy for us to kind of deal with them. If hydrogen's 1 electron is going to be placed in one of these orbitals, it's the only electron. We might as well put it in the happiest possible place, right? Let's put it in the lowest energy one. So that means, since it's only 1 electron, let's put it as close as possible to the nucleus. So we're going to go ahead and put it in the 1s orbital. We kind of draw these as boxes, and we draw electrons as these little half arrows. So I don't think I've used other colors today. The box is the orbital, and this little guy is how we describe the electron. So we're going to describe hydrogen's electron as being within the 1s orbital. It's hanging out in there. If we look at helium, we know that the 1s orbital is the lowest energy. It's the closest one to the nucleus. And since we know s orbitals can hold 2 electrons, we're going to see we can do the same thing. We can say, okay, we're going to put our first electron in 1s. Aha, our s orbital's still not full. We still have another electron. Let's put that one in there as well. And so we can see we can have 2 electrons can occupy this orbital. But we indicate that this is a little fun fact about electrons. They spin in different directions. Whenever two electrons are sharing the same orbital, they're going to have opposite spin. Don't worry about spin. We're not going to worry about that until 111. So you can kind of forget that. Just understand that if you're going to put one electron up within an orbital, the other one must go down. That's how we indicate the spins. And again, you can kind of forget about spin for right now. But suffice it to say, we can't have two identical electrons within the same orbital. And so if they're going to be kind of shacked up together, they have to spin the opposite direction from each other. Otherwise, their magnetic fields will mess with each other and bad things happen. So just suffice it to say, one goes up, the other goes down. Easy. That's the easy way for it. Alrighty. Let's look at lithium now. Lithium is 3 electrons. Of course, we would want to put the lowest ones into that 1s orbital, like before. And so we can do that. And if you look here, we'll end up having now 2 electrons in that 1s. But now we still have 1 extra electron that we're going to have to deal with. Right? We've used up 2 of them. We've put 2 of them in their happy little houses. And now we're going to see that, we're going to have to put the next one in another box. And the next lowest energy one will be the 2s subshell. So we're going to see that we're always going to order electrons from lowest energy to highest energy. And we're going to kind of be moving out from the nucleus as we do this. Let's skip ahead to, say, nitrogen. Nitrogen is going to have 7 electrons. Just like before, we're going to go ahead and fill up our lowest ones first. Those are going to be the 1s and 2s. We've used up 4, but we still have 3 of them left. If we go back, we see, in the n equals 2, we also have 2p. So let's go ahead and put that 2p orbital in there as well. A p orbital will indicate as having 3 boxes. One for px, py, pz. Remember, there are 3 of the p orbitals where they all kind of go in different directions. And we're going to see each of those p orbitals can hold 2 for a maximum of 6 for the entire 2p. Alright, and so we kind of have the option here. We can either do it like this, where we put 3 of them in that way. No, they can move. As you get to more advanced chemistry, you can see that electrons can move all over the place. So you can if you blast an atom with an X-ray, you can make an electron go from 1s to 5f. Go all over the place. So you can totally do that. So not necessarily, they're not confined within their shells. The more energy you give them, the kind of bigger gaps they can jump. Definitely there will be an energy gap between the s and p orbitals. Those are pretty small, but if you're going like between different shells, those require higher energy, so it is possible. We're going to see that this is not good, because we're going to want to actually first put off our electrons separately before we start pairing them off. Remember, electrons don't want to be near each other, so the better we can do to kind of keep them separated is kind of ideal. So this is now good, where we will have kind of separated them. So we have some vocab here. Since these three p orbitals are equivalent in energy to each other, they're equally distant from the nucleus, they're just arranged in different directions. We have we have a word called that these orbitals are degenerate. That means they have same energy. And so, because they have the same energy, we're going to want to, instead of pairing off our electrons, we fill them one at a time in degenerate orbitals. Well, let's see. Let's get rid of boxes. Fill singly. Singly. That's a new word. So, think of it as like a hotel or something. If these three electrons go to this hotel, there's 3 rooms. Yeah, why not get their own room, right? Nobody wants to be forced to shack up, right? So, let's have all the electrons be given their own room, and we'll start kind of filling the rooms with doubles afterwards. So we're always going to fill these kind of singly before pairing them off. All right. Ooh, look at all the stuff we've done today. I think it's time I teach you the tricks for not having to worry about doing this. So I think I said it like 10 times now, but we always fill lowest energy orbitals first, right? That's the big thing. So we're gonna see that in terms of shells, the first shell will always be the lowest energy compared to the others, right? It's the closest one to the nucleus. If we look at subshells, S subshells will always have lower energy than P, which will have lower energy than D, which will have lower energy than F. Okay, but so if we compare, we can say, okay, yeah, for sure 2s will be lower energy than 2p, and 3p will definitely have less than 4p. Like, not a problem. But if we compare these two and those two, it's not as obvious to us, right? We know the shells will have an effect, so the lower shell is ideal, but the lower subshell is also ideal. And we're going to see that in the case of the 3D orbital, it's going to have energy in between those two. The 3D is actually between 4s and 4p. And we can explain this using the periodic table. So we're not going to necessarily have to worry about that right now. We'll worry about that in a few minutes, but not right now. You won't have to kind of be able to figure this out on your own. I'm going to give you a couple of tools to figure this out. The first one, if we take this lovely thing that I've drawn previously, this one actually will tell you how to fill your orbitals. And how we do that is, let's see, what color shall we use? How about green? How we actually do this is if you draw diagonal lines through the orbitals diagonally, they'll tell you which orbitals to fill in what order. And so as soon as you reach the bottom of one diagonal, you'll go to the next one. And so let's go ahead and look at what we've done so far here. So if we're trying to look at the orbitals in terms of their energies, we're going to see that 1s is the lowest, then we go 2s, then 2p, then 3s. I'm just following these arrows as I've drawn them. So like after 1s, I went now up here, and now I'm crossing through 2s. And now I go back up here, and now I cross through 2p and 3s, then 3p, 4s, 3d, 4p, 5s, etc. But we can keep going from here. But this will always tell you the order from lowest to highest energy. So as we go through it, this is one way that students tend to prefer to use to figure out how to fill the electrons, or how to fill these orbitals with electrons, rather. I typically use the periodic table instead, but students typically find this one easier to use. So by all means, use it. And so, if we were to take a particular atom, let's say we have, I don't know, how about aluminum? Aluminum has 13 electrons. We get that from the periodic table. If we look at this order of stuff to fill, we can go ahead and kind of bring some of these down. We know we're going to start with 1s, which can hold 2 electrons. After that, we have 2s, and then 2p, then 3s, 3p, 4s, blah, blah, blah. Let's just see how many we can fill in this thing here. So remember, we always want to fill lowest energy to highest energy. I've gotten this order of them from our little mnemonic here. So we know we're going to fill them in this direction. So let's start filling them up. So if we fill our 1s, we'll put 2 electrons there. We have 11 left. Let's keep going. Another 2 electrons there. Got 9 left. 1, 2, 3, 4, 5, 6. Remember, P can hold 6 electrons. We have 3 left now. Keep going. Another S subshell can hold 2 electrons. We have 1 left, so we're going to put it in our last little box there. We would be able to write this out without having to use these boxes like so. Oops, 3p. And so we can see here that we have some ways of talking about these little things. This is going to be the orbital that it's in. And this number up here is how many electrons are in that orbital. And also note that the all of the orbitals here, except for the very last one, are completely filled. So we'll always completely fill we always fill the orbital before moving on to the next one. All right, and so this is called, by the way, an electron configuration. And so we're going to see that knowing the electron configuration is going to be very useful for us when we are actually explaining how things are reacting. We're going to see that atoms with similar electron configurations are going to behave very much the same way to each other. And so knowing the electron configuration, we're going to be able to predict how different elements are going to react. And that's the whole point of doing all this stuff. I don't think so. They can collide in probably crazy circumstances, but probably not based on two facts. That they're very small and that they're negatively charged. So if we think about it, to fuse two nuclei together, nuclei are much, much bigger than electrons. That's the process of fusion. That's what happens in the sun, where things are super high temperature, millions and millions of degrees. And so you can think that these very large, similarly charged things are coming together. But electrons being so small, just the likelihood of them being able to hit each other is just, super small. So maybe in some crazy circumstances they would be able to collide, but I can't think of anything normally where they would be able to. So they're just zipping around. They just don't hit each other because they're always pushing away from each other because they're negatively charged. So they're going to put out their electric fields, and those are going to repel each other. So they're probably not going to ever collide under normal circumstances. Alrighty, cool. If we look at something like chlorine, we can do that as well. Chlorine will have 17 electrons. We can kind of copy our same thing from before. And let's go ahead and fill this one up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Hooray. If we were to write its electron configuration, we would say it's 1s2, 2s2, 2p6, 3s2, 3p5. That would be chlorine's electron configuration. And so we're going to see again, we have all of our lower energy orbitals filled completely, and then we just have the last one which may or may not be filled completely. All right, it's time to show you another trick. Get ready for my lovely drawing. See, this one wasn't too bad. This is the periodic table, yes? And technically we're going to have this bit down here. But let's not worry about that right now. All right, it turns out that we can kind of make some characterizations about everything on the periodic table here. We're going to see that every element that is located in this portion of the, periodic table, that kind of two columns, is called the S block. And everything in there will have its last electron in an s orbital. Of course, it might be 2s, 3s, 4s, whatever, but it's something in an s orbital. That's going to be this section right here. We're going to see that this middle area is called the d block for the same reason. All of the elements in that section of the periodic table will have their last electron in a d orbital. On this side, we have the p block, and then down here we have the f block. Notice that helium here is special. Helium is actually still part of the s block, but it's just kind of arranged there because chemically it behaves like everything else in that column. So helium is kind of its own little section there. All right, here is... Oh my gosh. Oh, I'm tired today. That long weekend does that to you, huh? If we look on the periodic table, we're going to see we have 7 rows. And notice we also had 7 shells. Coincidence? I think not. These rows on the periodic table, called the period, will tell you the shell of that, or how many shells that particular element will have. So if we look at, I don't know, here's our aluminum. Aluminum is right here. Aluminum, we're going to see, is in period 3. So it should have 3 shells. If you look at its electron configuration, we just did this a second ago. This was what it was. Notice aluminum in the p block has a p as its last electron. And notice it's also in period 3. So note, for example, all period 3 elements in the p block have configurations ending in 3p. Amazing. Notice we had chlorine there. And we saw that it ends in 3p5. And if we want to look at this further, we know that the p block has 6 columns in it. Aluminum, being in the first column of the p block, ended with 3p1. Chlorine in that same block had 3p5. Amazing? Yes, I think so. Argon, therefore, we would expect, argon is over here, to end with 3p6, and it will. Amazing. So, if you just look at the periodic table, it'll tell you what the last electron is going to be in your particular atom. Yes, you certainly can. We call the boxes an orbital diagram, so like you may be asked for that on homework or something, so that's when you would do the boxes. But yeah, generally you're just going to be using the configurations. So you can totally skip doing all these boxes if you can just figure out what its last one is going to be. So let's take a look at, how about cesium down here? What do we think cesium's last electron is going to be? Well, we know it's in the s block, so it should have something to do with s. And we see it's in the 6th one Absolutely right. You're right. Absolutely. You did it, Eddie. It's in the first column of the S block, and it's in the 6th period. So we're going to see that cesium will end with 6s1. Absolutely right. Isn't that amazing? So we can just use the periodic table to tell us what the kind of last electrons are going to be in a particular element. So if we just put argon, that was 3p6, chlorine was 3p5. It is a good shortcut indeed. So the periodic table will tell you the last electron. Awesome. And then you just need to fill in everything before it. So if you look back to your handy dandy mnemonic and say you had something that ends with 5p, or 6s if we're doing cesium, we would just fill in everything before that. So everything that comes before 5p, we would just fill up to maximum. So we would go all the way through all of these other orbitals and just fill 5p. So we don't even need to count, if we were looking at, iodine or something. We're going to see we have we do have a trick, Eddie, to go through that. But it is not just ... Wouldn't that be nice? So let's do it. Let's do this cesium. This will be very exciting. So cesium, here we go. I don't even know how many electrons does it have. Let's see. Cesium. No. Cesium has 55 electrons. Oh, what the heck? Well, this is new. They've put an 8th period on the periodic table. That's absolutely crazy. Wow, this is brand new. I have never seen this before. Anyways, let's not worry about that right now. I see it's in 6. Oh, 55. Yeah. I thought you wrote 5s. Cool. So, wow, fascinating. So we have 55 electrons. No one wants to do boxes for this, right? No one's going to want to count 55 electrons. Forget it. So forget that. Let's not even think about that. Let's look at it the other way. Let's know we have to fill up to 6s1. And everything before that has to be filled completely. So, if I really should just copy this down here. Let's get rid of that thing around there. Yeah, let's just copy this guy. Actually, I might just have it still. Let's see. Oh, I do. Okay, cool. Let's move it down a little bit. So let's do this step by step here. So we know that we are going to end with 6s. So we're going to go and do our diagonal lines until we reach 6s. So 1s will come first, then 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s. I'm just doing everything that my little arrows go through. Then 4d, 5p. These are all the orbitals that are going to be completely filled until we reach 6s. And now, we just have to remember that we have the maximum number of electrons. And so we just need to put those on there. All the s's will hold 2, the p's will hold 6, d's will hold 10. We don't have any f's here, so we're okay. And boom, we're done. Easy. Quite a bit faster than doing boxes, I hope. And kind of putting them in that way. So we see again here, everything else is filled completely before this. Hooray. Alrighty. So this is how you will generate an electron configuration. There's another way to do it, though. This one I like, but some students don't like, which is, again, totally cool. Oh gosh, this periodic table is just even uglier. Technically, hold on, I might have to draw this one with the F block in there. So the F block that normally we just kind of put at the bottom technically goes in there, but it just makes the periodic table too long. So people usually just take it and set it at the bottom. But technically that's where it goes. It would go after the S block there. So we're going to see that we can just label all of the subshells on our periodic table. 4p, 5p, 6p, 7p. All right, so notice that the S and P ones are exactly the same as the shell they're in. So 1, 2, 3, 4, 5, 6, 7. Once we get to D, however, that's actually going to be 3D there, even though it's in the fourth period. It's still 3D. So D will always have n minus 1. So n will be the period you're in, and you just have one less kind of spot. We would then have 4D, 5D, 6D. And then we're going to see that for F, it's going to be 2 minus it. Yeah, only trust S and P shells. Yes, correct. And so if you were to go ahead and pick some element on the periodic table, let's say I pick whatever, what is this going to be? Iodine, I guess. If I pick iodine, we know iodine will end in 5p5. What we can do is just fill in all of the orbitals before iodine. And if you just look at the periodic table, it tells you exactly what to fill before you get to iodine in the order that you go through it. So we first went through 1s, then 2s, then 2p, then 3s, then 3p, then 4s. As we just go from left to right on the periodic table and then go down, like after calcium here, we now move to scandium in the 3D area, and then we move to 4p here, and then 5s, and then 4D, and then we end up in 5p. So this is another way to do it. If you just look at the periodic table, it'll tell you where all of these things are, as long as you remember the trick for the D and the F orbitals. You can do it that way too. So just looking at the periodic table, which blocks you go through, if you can name those correctly, you're going to get the right answer. And again, just completely fill these guys. And lo and behold, we'll have our answer there. Oof. So you will have a worksheet that will go over this thing. So you'll have plenty of practice in doing these. But I think it's time. It's end of class pretty much. So I'm going to teach you the shortcut now. This is kind of the expanded or standard configuration. But there is a shortcut, which we call the noble gas configuration. We're going to learn what the noble gases are in probably tomorrow. But suffice it to say that everything in this column is the noble gas. It's the end of the periodic table, right? It's kind of, the very last one in a shell. So we're going to see that we can kind of abbreviate these by using the configuration of noble gases. So noble gases, they end with something P6, whatever shell they're in. And so we can just say, okay, all this crap up to P6, this is just the same as a noble gas. And that noble gas happens to be krypton. And so we can just say, okay, everything that's filled completely up to this iodine is our krypton there. So let's just start with krypton's electron configuration and then move forward. So after krypton, we would then start our 5s, and then our 4d, and then our 5p for our particular iodine here. If we were to look at our cesium, we'll see that cesium, let's go back to where the heck we found cesium, the noble gas before cesium, in the row above it, is xenon. So cesium is even easier. Here was iodine. That's cesium's electron configuration in terms of the noble gas shortcut. So the noble gas will replace something P6 within your kind of expanded one. So if we go back to where we drew cesiums, we're going to see all this crap is xenon. And so we just have to put the last one. So using the periodic table is a little bit easier, in my opinion, for using this shortcut, because you can see exactly where the noble gases are and then just move on through the periodic table to get whatever's left. So we're going to see that that's going to be an easy way for us to just talk about the most important electrons. The ones that are going to be doing all the chemistry are going to be your highest energy ones. Those are going to be the ones on the outside of the atom. Those are going to be our ones in the highest shells. So with that in mind, we got through it. Hardest lecture, in my opinion, for the class. Hooray. Tomorrow we'll continue on this topic. We will probably meet on Wednesday or Thursday for just kind of a little bit of catch up, just because we're a little bit behind where I'd like to be at this point in the semester. So we'll have a stream on Thursday as well, same time. All right. Well, with that, I'll see you guys tomorrow. Enjoy your Tuesday, and yeah, I'll put up your worksheet so you can start taking a look at it. So, hooray. Have fun. Don't forget you have a couple of lab sims that are due this weekend as well. Hopefully some of you have already started on those. Those have been available for the past week or so. So they're going to be kind of dealing with the stuff about electron configurations and energy and that sort of thing. So just more ways of being exposed to the same material. So, cool. Alrighty. I'll see you guys laters.